Hey everyone, welcome to Glazing Talk. This is Alex Burchell, and today we're going to be talking about multi-span curtain walls. We got John from MP Drafting here. Welcome on the show, John.
No problem. Thank you for having me.
Absolutely perfect. So every company has to do these quick turn and burns, right? It's a lot easier to just go through a project, get done with it, move on and everything. But almost every large glazier is going to face some of these large buildings at some point. And I'm not sure if that's really where the money is, but the larger the buildings, I'm assuming the better the profits if done efficiently. That's, I guess, kind of what I believe, because most of these companies like to try and do bigger, better things. But today we want to talk about something that's going to be in line with one of our courses. And we talk about like large buildings and how they move and the fact that they're not just static. Not everybody might know that. You know, these things have to expand and contract based on the materials that are on them and so on. So we brought you on board to talk a little bit about some splicing that happens in these buildings that are kind of hidden. I do have a list of questions here that I'll kind of go through, but if you want to give us a quick little intro on who you are and your background, and then we can kind of dive into this just so our viewers can learn a little bit about you.
Yeah, I'm John Gurr. I've been here at MP Drafting for, I think, about a decade now. But I've done thousands of projects, a lot of multi-story spans. I'm the engineering manager here, and we've gone from start to finish on a whole bunch of jobs. So I've kind of seen it all so far. At least I think so.
Yeah. So you actually have engineering background, is that correct?
I do. I have a degree in civil engineering.
Okay, cool. So not sure anybody knows this, but John and I have some history. We've worked together in the past. We came from, or we started off in similar companies. Yep. Actually, probably the same company. I don't know if you had a different job before that.
So residential glazing we did.
Yeah. So it was a whole bunch of like additions, kind of like enclosures and so on, made out of glass and metal, much in line with this.
Not too many multi-story projects.
Yeah, there was a couple of larger pieces that we ended up doing. I'm not sure if you were around for like some of the really obnoxious pool enclosures that were happening over there, but we found quickly that they were not a good way to make money.
Yeah.
And unfortunately, some of our salespeople were a little less informed than we would have wanted to, because, you know, you spin fans this way and the other fans this way, and suddenly you don't have any steam in a pool, and that's not... Anyway, we won't even dive into that. But I want to get into some of these questions because obviously that's what we're here. We want to get you to give us some information, or at least our listeners, our viewers, whoever's watching this. So the first one I have here, and this is kind of a big deal, and I touched on it briefly here, is, you know, you got movement in a building. And how much does the building really actually move? I mean, what are we talking about here?
When we engineer things, your options are either bend or break. And so things aren't rigid to a point of not movement. I mean, there's not tons of movement, but you'll have skyscrapers that move, 6 inches on a calm day. But like the Mackinac Bridge moves like 10 or 20 feet, I think, in either direction in heavy winds. There's considerable movement in these structures, but they're designed to move that way. And so that's what we do when we set up these shop drawings and make sure that we can handle all the movement.
I want to talk a little bit about what that movement means. So you mentioned the Mackinac Bridge. We have a really long span. We're talking that it's going to wave left and right, or if you're on the bridge, up to 10 feet is what you just said. So when we're talking about a building movement, are we talking about the top of the building is going to sway back and forth? Are we talking that it's going to go up and down?
Yeah, so we have, there's all kinds of different load movements we have. Dead load movement is just, that's the weight of the building. It's when it goes in, the bottom floors are going to end up taking more and more load, and they're going to have some kind of settling movement. But live load is things like wind, snow, the people walking around on the inside floors. All of those things come into consideration. So yes, in the wind, you're going to have a building that will sway side to side. It might twist a little bit, but there's also vibration in the floor. Sometimes you can feel it. Like if you close your eyes and stand like kind of near the edge of a long span, you'll feel some slight vibration. And what we do is we make sure that the movement is mitigated to the point where people are still comfortable in that building. If you have a floor that's jumping back and forth 3 or 4 inches, no one's going to want to be in that area.
So if I was in an office building and the 15 of us decided to run from side to side, we could definitely give some motion to the people below us. Is that what we're saying?
Yeah, I mean, you can. I'm sure your lower tenants would probably give you a phone call, but yeah, I mean, we're not going to knock ceiling tiles down on them. Again, it's all mitigated in, and all the loads are accounted for in a worst case scenario. So they're ready for that New Year's Eve party. When you have 1,000 people on your floor. That's what everything's designed for. It's never designed for just everyday use. It's always worst case scenario.
Okay, so obviously it's designed to the point that a lot of us didn't even know that was happening.
Sure.
Right? So that's pretty impressive. And then you're going to design based on different areas and zones, right? I mean, if you're in California, you got earthquakes to account for, whereas over here in the Midwest, we got a lot of wind, a lot of snow.
Or if you're in Dade County, we're worried more about hurricanes and earthquakes. Not so much snow,
So the designs in particular are based on location?
Absolutely, yep. There's regional maps for all the different things, wind, snow, earthquakes, all of those different loads will have a contributing factor, and then there's always going to be one that stands out the most. Typically, for the glazing systems, we're worried most about wind, just because, I mean, we're kind of like a sail. When the wind blows, it's going to hit the glass, and it's not going to go anywhere. It's going to put all that pressure on the glass.
So the building footprint itself, taller, thinner versus wider, it all comes into play.
Absolutely.
Okay. That sounds like a pretty mathy job right there. That
yeah.
I'm sure as an engineer you love. I wasn't a big friends with Math H in school too much there. But all right, let's talk a couple of different things here. So who's going to make this decision? Is it the engineer's responsibility ultimately? Is it the drafting company have to catch some of these things to verify because they know the products maybe a little more than the engineer? Is it a communication between, or is the architect at the beginning kind of ultimately responsible?
So the architect at the beginning is going to have some general knowledge of building movement and what he can expect. Okay. Then you're going to have the building engineer who he's going to talk with all the different trades and make sure they all understand what's going on. After that, it's going to go to the different trades. The steel guy knows exactly what his limitations are, the concrete, the foundation guy. And similar, the glazing systems, we have our own limitations that what we can expect and what we're limited at. I mean, our glass is, I believe it's 3/4 of an inch. We can't have any more movement than that, period. Wow. And so when we design things in, the engineer double checks it and makes sure, hey, this is moving too much. I can't have that. Even if the building's going to move more than that, you go, well, ours can't. And so we make sure that ours stays within the limitations that are allowed to us by the code, and we go with that.
So each individual product and piece has its own rules.
Yeah.
But then the combination of them ultimately have a giant rule.
Well, so what happens is you'll have all the materials that have different properties, right? So you have steel, which is very strong, but it also can be very flexible. And so it can move quite a bit. And we have plastic and elastic deformation. Plastic deformation means it's going to stay deformed. Elastic is it kind of bends and wiggles a little bit, but it goes back to normal. Okay. Steel has a lot more elastic deformation than, say, masonry. After masonry starts to move, I mean, you got a big problem. You're going to have cracks in your joints and things, and it's not going to be okay. We're dealing with aluminum and glass, and so the glass is going to be your fact that you have to take care of the most. But that aluminum can move quite a bit and still be okay.
So you and I have had conversations in the past. I remember from our previous years that we were talking about concrete, not related to what we're doing right now, but you kind of brought up some masonry. So I know that they test the strength of that, right, every single time to make sure that there's a certain consistency or so on. Anyway, not where I want to go with it. Are they doing the same thing for all the other products? Does glass go through some sort of testing that you know of, or the metals themselves?
Yeah, all the engineering handbooks, depending on what material you're using, there are safe assumptions to use, and we plug those in for modulus of elasticity and things like that we know how much it's going to move, or we can. Between the factors of safety and the equations we use, we know that we're within a good range.
That's awesome. Okay, cool, very cool. Thank you. Let's move on to something that's very important. So we're here because we're talking about multi-story. So we're talking about spans, right? And the mullions are limited. They're going to come in a certain length period. We know that that's what's, they come in 20 feet or 24 or 30 or whatever it is that you're buying. Buildings are taller than that. So what happens when a building is taller than that?
The short answer is we stack them up like Legos. But no, what happens is you're right. They do come in. A standard length will be 24 feet. You can order them a little bit longer, but you can't get an unlimited length of material. And so if you have a 60 or 70 story or foot tall building and you need glass that tall, you'll take those 24 foot lengths and you make a splice joint, and we stack these things up. There's usually multiple anchor points that they'll have to dead load it at certain floors as opposed to a wind load, so that it can't come down any lower. And we account for that building movement. One of the other movements we have to account for is temperature movement. In the summer, the buildings will actually grow a little bit. All the material does.
Expand.
Yep. And in the winter, they're going to shrink.
Yeah,
and
when it gets
contract.
cold outside,
Yeah.
they shrink a little.
Just a little bit. But no, we account for those movements. And so, if you have, like, say here in Michigan, it was -10 last week, and it's going to get to 100 this summer. So you have to account for 100 degrees of different temperature, and that's going to make your metals expand. And they might only expand a 1/4 inch or 1/2 inch, but you got to be prepared for that.
Well, I mean, it doesn't sound like a lot, but if you have 17 of these things on top of each other, it just
Right.
turned into a foot, right?
Right, and that's probably where we're going with this, is that obviously the architect doesn't want just a 1-foot joint at the top of his curtain wall.
Right,
That's
of course
going to
not.
be an issue.
Yeah, so you're just separating these, kind of staggering them up and all that.
Right. Yeah, so we can take care of that movement throughout the building all the way through. And so we don't have one big joint at the top. We can stagger it and have it partway through and just pick up that movement along the way.
Now, I'm going to make a silly assumption here because I don't know any better, and you're going to correct me. Would they all expand the same, or are we talking like the bottom floor could take a little bit larger expansion, the top one's a little less? Are they all independent?
Yeah, they're all independent. So what happens is if we just take, we'll say a 20-story building, and we're going to dead load it every other floor. And so if we dead load it at the even floors, 2, 4, 6, 8, 10, floor 5 can move completely independent of floor 4. Maybe one of them has a swimming pool on it, or there's a lot of foot traffic on one that's not on the other, and we're expecting that slab to move more. That's a very real thing. And so as long as we've accounted for that movement between the dead loads, then everything's going to be just fine.
That's really interesting. I never really, I guess, thought of the different things that could be on the different floors. I just, in my head, every floor has the same furniture, right? Just
Right.
Yeah, but a swimming pool is an awesome example. That's pretty cool. Yeah, that's cool. And I'm assuming temperature could be different too, right? You're talking, if you're 100 stories up in the air, the temperature could be different than if you're at ground level.
Sure. Well, it's not only the temperature, is the wind loads actually increase as you go up.
Yeah, you did mention the wind was, yeah.
Right. But I mean, at the bottom, imagine if you're in New York, the first few floors, you're surrounded by other buildings, everything's in the way, you're not going to have heavy wind.
Sure.
But if you're having a heavy storm and there's 100-mile-an-hour wind, if you're the tallest building in the area, you're taking the brunt force of it at those top floors. Bottom floors, maybe not so much, but it makes a big difference.
Yeah, I've always been curious. Some of these buildings are going up. They're taller and taller and taller. Like Dubai has some incredibly tall buildings. Just, I wonder if you just like are swaying up there. You feel like you're on a boat all the time.
I got to imagine. That's got to be...
Yeah, it's just like a cruise.
Yeah.
You live in a cruise. That'd be awesome. John, awesome. Thank you. I'm kind of learning a lot here. And we do have a course that talks about these different splices and so on. And you said dead load a second ago, right? So there are multiple ways of splicing these things together. And you've explained this to me in the past. Could you give us just a quick rundown of like the different ways that you can do that?
Sure. So when you're splicing these, we got 2 different kind of splices for the most part. We have a working splice and we have a hard splice. And so if you've only got, let's say it's a 35-foot tall building, and the architect says, what's our total joint? It's 1 inch, and he's okay with that at the top of the building. Then you can splice these 2 together, and really you put a sleeve inside the mullion so they can't move back and forth. They have to, stay together. If you want a hard splice and you take these things all the way to the roof, you can make that seem as if it's a single mullion,
Okay.
and go all the way up. However, if the joint's too big for him and he says, no, I don't want that big ugly joint at the top of that, what else can you do? We do something called a working splice, and that's when you still have the sleeve, and so these things are going to move together laterally. But what the sleeve does, if you do a working splice, is you only anchor the sleeve to one side of the mullion. And so that sleeve can slide up and down the other one. So when there is movement, even though they can't move laterally different than each other, it can move vertically different. And so what would happen is you would dead load, and there's dead load and wind load. Dead load is when you hold something fast to a floor. It's not moving, period. You've bolted it to that slab or whatever it is, and your system has to move with the slab. If you do a wind load allows the curtain wall to move independently of the slab, and it gives it some wiggle room. It can move up and down as that slab moves, so there is some independent movement. And so if you have a working splice, you need to have a dead load joint or a dead load anchor with that, so that they can move independently. So that way your bottom floor and your top floor can do what they have to do, and you can break up your joint between that dead load and the working joint and the head joint.
Okay, so if I understand this correctly, we have a curtain wall because it wouldn't apply on storefront.
Right.
And on the inside of the curtain wall, the curtain wall has a hollow, like a beam in it, built into it,
Right.
we'll say. And inside of that, there's a smaller beam
Yep.
that's just going to go a foot up and a foot down in between the two, or whatever number that may be.
Sure.
And one of them is bolted in, the other one is slotted, a
Right.
bolt as well, but it can travel up and down on that little slot from one to the other.
Yeah, you don't even have to bolt it in the one that's not held fast. I mean,
Oh.
if it's inside that sleeve, there's nowhere it's going to go anywhere.
Fair enough.
It's a pretty tight connection. So I mean, you're going to have very little movement back and forth. But what you want it to do is be able to move up and down without issue. And that's it.
Okay, so there's probably some obvious criteria to make sure that it's tight enough that it can stay and not wiggle around, but loose enough that it's going to move without grinding everything?
Yeah, these are all standard extruded parts. I mean,
Awesome.
They're straight from the manufacturer. There's no question that they're the right size, the right shape, everything that fits really nice and snug.
Okay, so you're ordering the parts, and they have their catalog available with these parts as well.
Absolutely.
That's good. Excellent information. So whoever you use, they're going to have their own catalog.
They're going to have everything you need. Yeah.
Excellent. So we talked a little bit about how the splices work, and I had a really weird question. There are those structurally glazed systems, right? Structurally glazed systems is when you don't see the visible mullions on the outside of the building. When you're channeling, and we know that all these systems are designed to channel water and move up and down and so on, what happens in a structurally glazed system in terms of movement? Are we just relying on the silicone to move up and down and expand, or?
Right. So in a standard capped system, the ones you can see, what we use is gasket. And so when we have these splice joints, we will stagger the joints between the inside mullion and then the pressure plate, the face cap, all of those things, so that water can work its way out. But because we have some leeway, those gaskets are flexible. The building can move, and we can put those splices almost anywhere. We usually try to hide them in between floors or out of the eyesight of where people are walking, because there is exposed fasteners usually. But in a structural glaze system, they're glued hard to the fasten or to the mullions, and so we can't just put a splice in this thing and then hope the top and bottom, don't move enough to break that silicone splice. That's a problem. And so what we do is the main mullions and the verticals in the back, they do get spliced very similar. There's a sleeve, they get bolted together, everything works fine there. But when it moves out to the glass, it gets more complicated because that silicone has to stay hard to those mullions. And so usually there's a horizontal splice joint, and it's like two horizontals that come up against each other, but there's a splice there and it's hidden. But it gets much more complicated when we're dealing with the structural.
Yeah, it sounds like it's a completely different level of like, hey, I'm just going to buy some pieces out of a catalog. Now you're definitely having to consider a lot more things.
There is more to consider, and you definitely want to get your engineer involved early, so that you can plan those out and make sure that the architect is okay with where you're putting your horizontal splices, so that he knows there's going to be a stack joint there, and it's not as open to just put your joints wherever you want, like in a cap system.
Okay. Yeah, I mean, also everybody's looking for a clean system, something that looks really sleek. I've seen a lot of these buildings that are just glass top to bottom, and you got to start asking some of these questions, right? Because there's so much involved behind them. I mean, when you can see the mullions, and once you learn about them, you understand how they interact. But you start seeing stuff like that, it just it sounds like trouble for a lot of people just to make it that pretty.
Yeah, I mean, and that's what everybody wants. I mean, this is the part you're going to notice the most. This is what people recognize when they see a building. If you see the shape of it, you can identify the CN Tower, different very fancy buildings that are
right.
Famous all around the world. No one knows them by their structural steel. Everyone knows them by how they look and how the glass is on them. And so you want something that looks clean. And that's why when we do splice these things and we do stack things up, we try to keep those joints in spandrel areas, hidden areas, in between floors, above ceilings but below floors, just to keep a clean look.
Yeah, it's funny because as we talk about this, and as I was learning about this myself, I have to be honest, I don't think I've ever noticed any of these splices. I haven't had that forethought to look for them, even though I now know they exist. One of the things that I joke around a lot, and my wife would hate me for it, is that it doesn't matter where I go, I can't stop looking at this glass, right? I can't stop looking at all these things, and constantly looking for things that are right, things that are wrong, the polished edge or the holes or the graphics on it, whatever it may be. I'm constantly analyzing everything. I'm at the mall and stuff, and she's really annoyed by it. But I've never looked for these splices, so it sounds like these are just designed pretty damn well. It works.
Well, and again, that's it's a choice between the architect and the engineer, because you usually want to splice these things near an anchor, just because you want to make sure it's as structurally sound as possible. But the architect has a lot of say in it, and I mean, we all know that. And speaking as one, architects may not always have the most aesthetic mind when it comes to design. They just want it to work.
Yeah.
But the architect is also integral in making sure that, hey, we're going to hide these things. We got to make sure that the building looks clean at the end of the day, and that's what we do.
Yeah, I have my experience with visiting architects and talking to them and about designs and so on, and it feels like the overall mission is always the same, right? I definitely want it to work, but I have this vision in mind. This is what I want it to look like. Now let's meet in the middle and help me get that vision realized.
Sure.
Right, and that's where they're very flexible in regards to, like, I know that you know more about this than I do. Can we still achieve what I would like for it to look like? So
absolutely, and that's what we're all looking for at the end of the day. Is no one wants to walk away from a project knowing that somebody's unhappy with how the design turned out.
No, of course not. Yeah.
And so we all work together to make sure that we meet the design intent that everyone's going to be happy with.
So you work with MP Drafting, you mentioned. So I know MP Drafting is a firm here in Michigan, does a lot of shop drawings and all that stuff. Would you say that, and my understanding is that you handle all the special projects, like you're a part of the special projects group, the really complex and high-end stuff. So is this kind of like your day-to-day, all these splices and everything like that, and some of the other complex stuff?
It's not day-to-day, but I think I get them more than most people in the office.
Okay.
Yeah, it's after you do a few of them, it's fairly, as long as you have the knowledge base to do that, and you know what to look for, where the issues may arise, it's not a big deal. We can handle just about anything here.
So is that part of your service? You're the one looking for these potential issues? Are you communicating with the architect? Are you communicating with the glazer, with the engineer? Yeah,
so when we get the shop drawings, a lot of times in the initial set of architecturals, not everything is 100% laid out. You're not going to have an architect give you...
It's design intent,
give
right?
you his construction set, and it's going to like point right to a spot and and this is where the dead loads go, and this is where my joint goes. And so what we do is we use our best guess and say, hey, this is the design that we've been given, and this is how I would design it. And then when we send that to the engineer, we let him know that, hey, we're trying to make sure that these joints and dead loads and wind loads are going to work. What do you think? And then he gives us feedback, and we go back and forth between the architect and the engineer to make sure that at the end of the day everyone's happy. I mean, there's always a reason that the architect may reject our design. If I go every other floor and say, hey, this is what we've done, and he says, no, I'm going to dead load every floor because I want a very small joint at the top, and I don't want anything expanded, and I want A, B, or C. Hey, it's not a problem. We'll change our design to make it exactly what you want. But there's always somebody that has a reason why they would like it a certain way, and we'll do our best to work within those parameters.
So you've mentioned this a couple of times, and again, since I've never seen one because I'm not looking at these buildings this way, you've mentioned at the top. So what am I expecting? Am I saying that the mullion is going to stop about a foot short of whatever cap is at the very top?
Yeah. Well, so that's the problem is that when we have a system, you have to account for that thermal movement.
Right.
And so the taller the system, the more thermal movement you're going to have. And same with the floors. If we have to account for 5/8 of an inch of movement on every floor or whatever else has to happen,
wow.
If you let those all stack up, it's going to be a big problem. And so what we do is we determine how much movement we're going to have and whether or not it's going to be smart to splice it in one place or another. And when an architect looks I had an architect one time, we had a 30-plus story building, and at the top of this one, we had like 1.5 inch joint is what we're going to end up with. And even 30 stories up, he was like, no, someone's going to notice that. And I'm like, that's 300 feet in the air, man.
Wow.
And he was like, I'm not going to have 1.5 inch joint. So we said, okay, well, let's see what we can do with the design.
1.5 inches. I'll hold this eraser up here. Tell me if you can see it.
Yeah, but again, though, it's he knows what he wants.
Yeah.
And so we say, okay, well, we tried doing it this way, and he flat out rejected it. And we said, that's not a problem. And so I think in that one, we had just broke up the floors and just dead loaded at every floor for him and brought his joint down to a 1/2 inch or something reasonable that he was happy with, and we were good to go. But these are the things that there's communication back and forth. We make sure we keep everyone in the loop as much as possible and point things out, because that's our other thing that we do is when things do look out of place, we got to note it on the shop drawings, and we let everyone know, like, hey, here's a big red flag. If someone could take a look at this,
please.
I've given it my best eye, and I'm not sure if I have a solution for it off the top of my head. Maybe someone else knows what's planned here, because not everything is always planned from the beginning. Sometimes we throw up a red flag, and some people go, oh, yeah, we've been thinking about this for the last 3 months. Other times they go, ooh, no one's even looked at that yet. Let me give it a shot around the office, and we'll see what we come up with. So
yeah. So there's got to be some sort of balance too. I'm as we're talking, my head's just developing dollar symbols here. So if I'm going to splice this at every single floor, I'm going to order this many more parts that if I were to just accept a slightly larger, joint at the top. How does that balance? Because I know that everything's on budgets, right? So you say, yeah, absolutely, you can have them at every floor, but you're also going to order 600 more of these pieces.
Yeah, I don't know if that's too much of an issue, especially in a large project. You already have in your budget, and that comes down more to your efficiency software for when you're cutting your stuff up. If you're getting 24-foot lengths, and you know that you've got 12-foot spans between floors, you're gonna be okay. You're gonna cut them in half. But if you're ordering 24-foot lengths and you've got
13-foot spans.
13-foot spans. It's a problem. So at that point, you would know to, like, hey, instead of 24-foot spans, maybe it's better for me to special order 26 and a half foot spans, so that I get the best use out of my mullions rather than cutting one and then going, oh, and I hope I can use this 9-foot somewhere else. It'll be something that their cutting software or whoever's going through it to try to find that out. They can plug that in and say, hey, it'd be a lot better if we order different stuff. And that's just an efficiency thing, though.
So we were talking about these little sleeves a little earlier. Do these sleeves also come in those lengths? Are we cutting those as well, those internal pieces?
You can. I believe they sell them either pre-cut, or you can order the full extrusion if you'd want.
Okay.
But yeah, same thing. They're all extruded parts. So
yeah.
if you need them in 24-foot lengths and you want to cut your own splice sleeves, because maybe their standard one comes 30 inches, but the engineer says he'd like to see them 36. So you go, that's fine.
Wow, 36. Yeah, that's good.
Yeah, a foot and a half in either direction to just make sure that you've got a lot of aluminum in there that's not going to shear off or buckle. So.
Yeah, I like the make sure word. Make sure is usually good. I have one last question for you here, John, and thank you for being on the show so far. We have unitized systems. They're a part of our world. They're growing. It's a very efficient way to get buildings up fast. It's a lot of pre-work, in the shop. These guys are buying equipment and growing, so they can just get on site with less guys, one big piece of equipment, and just go to town and put entire floors in at a time, right?
Right.
Wonderful thing. But these have to splice.
Yeah, and so this is going to be very similar. And people that aren't familiar with Unitized, they're built almost entirely in the shop. They come out pre-glazed. They grab them with a crane, put them in place, anchor them down, and just keep on going.
Yeah.
There's no on-site glazing, maybe a few pieces, but for the most part, they go up real quick. In these systems, all they do, they're stack joints, and it's very similar. The splice sleeve is already in the one side of it, and so they bring it up with a crane, make sure everything's lined up, drop those splice sleeves into the floor below it, and just keep on working.
Wow. Okay. Yeah, I mean, I've seen guys out there. I got to go to one hospital job that was being done or remodeled not too long ago over here, and I got to say, without the prep work of like putting it on the crane and hoisting it and moving it up, I mean, these guys were locking these things within a span of 5 to 10 minutes, and it was time to get the next one rolling, right? And you're talking 20 minutes per piece just because they have to move it up 5 floors.
Right.
So that was impressive to watch them go that fast. So all these anchors are being pre-installed into the building, right?
Right.
And then they're just coming in and just tightening a couple bolts, and everything's all designed and set. Yeah,
they tighten bolts. The bolts are designed to level out because obviously not everything's going to be as perfect as I see it in CAD or in architectural drawings.
What do you mean?
Yeah, there's you account for human error, and so what happens is they have basically these giant set screws, so that if you've got to even it out by a 1/4 inch, maybe it's the slab was slightly tilted or an anchor was set in and it's 3/8 of an inch low. They'll just put these set screws in and screw it down until the whole thing levels out, and they're good to go. But I mean, they can do that with a power drill, and it's really an amazing process.
So every floor or every unitized system, because I don't know if there's multi-story for unitized systems, every single one of them is independent. They all move on their own. They all have their own kind of joint kind of worked into them.
Yep, and they're all set up. And like I said, if they do splice together, it's already pre-installed in the one. They come out, drop it right into the other, and can keep on moving.
Man, that sounds fantastic.
Yeah, a lot of work that goes into those. So in the shop.
Yeah, no, that's. I visited a local shop, and it was impressive to watch them build them, and it was impressive to see all that. And obviously, there's advantages and disadvantages. The advantage is the work out on the field. Disadvantage is you better have a pretty big warehouse and some good equipment and a way to get it on site. And then once they get on site, you're going to have somewhere to put these things, right? Because you can't just throw a whole bunch of cardboard boxes with tubes in it that you're going to hand cut. Like you're talking full finished units.
Right.
That's heavy equipment and some skill involved. You got to trust some people.
Yeah, and good information when they start, because if your shop drawings don't match the real situation, that's another situation out there.
Yeah, that's a fun conversation with as-built dimensions versus on-site and all that. That can get really hairy too. And it's funny how, like you were talking about precision in CAD, you can work up to, I don't know, easy a 64th of an inch, right? That's like almost an easy setting. Most people do like a 16th to a 32nd. You can go way beyond that. I mean, in the field, you grow a 16th of an inch per unit. By the time you get to that last one, you're off a couple inches and you got a problem.
Just a bit, yeah. Yeah, my old highway design teacher always told me, it's like, we designed to 4 decimal places in the classroom. We knock it down to 2 for the paper, and then the guys out in the field, if they're pouring concrete, they get to the nearest foot, they're happy.
Yeah, that's it. Yeah, I've been on some of these roads, I feel.
Yeah.
John, this is excellent. Thank you for coming on, and thank you for giving us some time to you, and obviously your expertise on this. Is there anything else you'd like to say, or anything you want to say about your company, or anything like that at all? Or
no, it's good talk. And if anybody needs shop drawings,
yeah, absolutely. MP Drafting. I'm going to blast that name all the way across the bottom here. I'll put your full name and everything. That's really good. I really like when you guys give us the time to come support. Obviously, this podcast, as well as the information that are useful for all of our students. So,
sure, not a problem.
Excellent. Thank you, John. This was a great time.
Yeah, thanks a lot.
All right, bye.
Bye.